Welcome back to The Explainer. Today, we're diving straight into some massive AI news, and I am absolutely thrilled to share this with you because we're looking at something that is actively reshaping how developers and engineers build AI systems. Look, if you've spent any time at all working with large language models, you already know they're incredibly capable. But they have this massive, glaring Achilles heel when it comes to fact-checking. So today, we're exploring a complete paradigm shift in how we build AI verification pipelines. It's all centered around a brand new framework called Evidence Chain Evaluation, or ECE for short. So to really understand why this is such a huge breakthrough, we first have to ask a pretty fundamental question. What actually happens when an AI is forced to guess on really weak evidence? Think about it like forcing a student to take a multiple choice test on a subject they've literally never studied and forbidding them from leaving any answers blank. I mean, they're gonna guess, and occasionally they'll sound incredibly confident doing it. Well, this is exactly what happens with current large language models. They generally achieve strong fact-checking accuracy, sure, but they are often forced to make binary true or false decisions. And this creates a major hidden reliability gap. The system is just going to issue a highly confident verdict, even when the supporting evidence it found is totally sparse, weak, or completely inconsistent. And that brings us to the core problem, and more importantly, the solution. Standard systems are rigid. They force a binary output, just true or false. And to cover up the fact that they might be entirely guessing, they tend to hide that uncertainty behind inflated confidence scores. But the evidence chain evaluation framework introduces a third, absolutely crucial option: uncertain. Instead of a forced binary guess, the ECE framework allows the system to actually evaluate the chain of evidence. And if that evidence fails to meet strict reliability thresholds, it simply outputs an uncertain verdict. Okay, let's dive into this and see exactly how we solve this binary guessing problem. We're going to cover the hidden reliability gap, introduce evidence chain evaluation, look at the selective accuracy trade-off, peek inside the evaluated architecture, and finally, talk about how to actually implement the ECE framework.
Starting with Section 1, the hidden reliability gap.
Standard retrieval augmented generation, or RAG pipelines, and automated fact-checking systems are basically operating on a fundamentally flawed assumption. They assume that every single claim requires a definitive label. But that completely fails under conditions of epistemic uncertainty. Basically, situations where the required knowledge just isn't out there or it just isn't reliable. So the key to fixing this is this concept right here: abstention. This is really the anchor concept for our entire explainer today. Abstention is the act of permitting an AI verification agent to return an uncertain verdict rather than forcing a low-quality prediction when evidence is weak. It's a safety-oriented mechanism. Instead of hallucinating a super confident true or false, the AI is given permission to just say, hey, I don't have good enough data to make a call here. Moving on to Section 2, introducing evidence chain evaluation. So this brings us to a recently published framework details in a really fascinating new archive paper by researcher Dudarik Yang. It introduces an evaluated architecture that operates as a tool-using verification agent. And what's cool is how this agent actively gathers evidence through 3 parallel channels. It searches the general web, it queries scholarly databases for academic sources, and it even performs executable checks. But here's the best part. Once it collects this evidence, it doesn't just spit out a generic probability percentage. The agent synthesizes its findings into a highly structural verdict that contains a confidence score right alongside source-level metadata. This metadata actually tracks the provenance and reliability of the evidence. And that is an absolute game changer, because it allows downstream systems to make hard, deterministic routing decisions, rather than just crossing their fingers and blindly trusting an opaque model probability. All right, Section 3, the selective accuracy trade-off. Now, what's really interesting about this is that the researchers made a deliberate choice. They chose to sacrifice aggregate calibration metrics just to prioritize precision on the claims the model actually chooses to answer. Looking at the benchmark data, when tested on the ECE bench dataset, the system achieves a 91.6% standard accuracy and maintains a 93.7% coverage rate. So this proves that even with the ability to abstain, the ECE baseline remains highly capable overall. It isn't just refusing to answer everything, it's still tackling the vast majority of the claims it sees. But wait for it, 97.8%. That is the system's selective accuracy on answered claims. By allowing the system to drop its coverage just a tiny bit, basically giving up on that last 6% or so of really sketchy claims, precision just skyrockets to near-perfect levels for the claims it does answer. Now, yes, the framework doesn't technically outperform retrieval baselines on uniform calibration metrics like the Breyer score, AURC, or expected calibration error, but that trade-off, completely intentional.
In high-stakes decisions, you absolutely want near perfect precision, even if it means routing a few more claims over to a human for review. Let's actually look at the proof for this. Out of 95 test cases on the benchmark, the system chose to defer exactly 6 of them, routing them straight to that uncertain state. And if we break down those deferrals and map them to an L1 to L4 evidence taxonomy, it is incredibly revealing. These deferrals are definitely not random. 5 out of the 6 abstentions were triggered at the L4 tier. That's the absolute lowest reliability tier in the evidence hierarchy, which typically includes stuff like unverified forums, conflicting reports, or outdated archives. This perfectly confirms that abstention is doing exactly what it's supposed to do as a safety mechanism for epistemically weak evidence.
Okay, Section 4, Inside the Evaluated Architecture. So we know the theory works, but how do developers actually use this structured verdict format day to day? Well, it allows for 3 massive architectural improvements. First up, confidence routing. If a claim returns an uncertain verdict, you can automatically bypass your publishing gates and just route it to a human specialist or just quarantine it. Second, source tier filtering. Because you now have that L1 to L4 metadata, your pipeline can dynamically weight the evidence. If a claim relies heavily on an L4 source, your system can automatically reject or escalate it. And third, executable verification fallback. If your web or scholarly searches yield really sparse results, the agent can trigger executable checks. This drastically reduces hallucination rates, especially when you're working in highly technical or data-heavy domains. And hey, this isn't just theoretical white paper stuff either. There is an active repository, Cheshire Yang/ECE, right on GitHub that provides a reference implementation. In fact, a recent MVP update shows they've already updated ECE/models.py to include a brand new reasoning attribute. So now, if the model detects an error in the input or needs to somehow correct itself, that explanation is explicitly captured in the reasoning field and printed out clearly. They've even added controls so that outputs over 500 characters automatically write to a file, rather than just totally clogging up your console. The point is, this is a highly tangible, usable tool that developers can literally grab today. And finally, Section 5, Implementing the ECE Framework. If you're out there building verification pipelines for compliance, content moderation, or even just standard RAG applications, here is your playbook. Step 1. Head over to the repository, clone the codebase, run the ECE bench suite to see it for yourself, and definitely make sure you pin your verification agent dependencies to avoid any breaking changes. Step 2. Implement that confidence-based routing in your orchestration layer. You want to set hard thresholds. For example, tell your system to only automatically accept claims with a confidence score greater than 0.85 and a source tier of L2 or better. Step 3. Map your own organization's internal source reliability tiers directly to the benchmark's L1, L4 taxonomy. But I want to give one really vital piece of advice here. Do not treat ECE as a simple drop-in replacement for your existing retrieval baselines. It is fundamentally designed to be a safety layer. You should integrate it right alongside your primary pipelines. And keep an eye on those abstention rates, because if you see a sudden spike in L4 abstentions, that is a fantastic health metric warning you that your external data quality has suddenly degraded. We've covered a ton of ground today, but as we wrap up, I want to leave you with a slightly provocative question to consider regarding your own architecture. If your AI verification pipeline currently hides uncertainty behind inflated confidence scores, what else is it hiding? By forcing developers to confront the reliability of their evidence sources directly, this evidence chain evaluation framework isn't just improving accuracy, it is forcing much-needed transparency into a notoriously opaque process. I highly encourage you to go check out the archive paper and the GitHub repository to see exactly how this can secure your high-stakes pipelines. Thank you so much for joining me on this explainer, and I will catch you on the next one.